Let's talk about basic SQL concepts. Structured Query Language, or as we pros call it, SQL. If you're going to be working with data, SQL knowledge is an essential skill to have even in the era of big data. Big data is often stored in what's called a NoSQL database. These databases are radically different from the relational databases that we've been dealing with for the past 30 years. Since a lot of big data is unstructured, it doesn't make sense to store this data in a structured way. There are technical challenges with trying to store so much information in the same way we've done it in decades past. These new databases also needed a new way for users and developers to interact with them. This has resulted in a paradigm where these new databases frequently have specific languages to interact with them that looks absolutely nothing like SQL. That presents a problem. Obviously, your initial cadre of big data professionals comes from an existing base of people who have been working with relational databases for years. There is a vast pool of people out there who know SQL. If you're trying to gain broad adoption of new technology, the best way to do that is to leverage existing skills. As a result, there's a lot of focus on developing software that allows people to query big data with their existing SQL skills. Apache Hive is one of those pieces of software. If you get a chance to play with Hive, you'll see that HiveQL, the query language used to interact with Hive databases, bears a striking resemblance to SQL. SQL is one of the first programming languages I learned. It's also my most used programming language. It's incredibly easy to learn. Every single SQL statement starts with 3 words: select, from, and where. Select the columns that you want. From the tables that you want them. Where the data meets these filter criteria. If you understand that, then you're halfway home. When I give lectures, you'll frequently hear me use the phrase the old world and new world. The tools and techniques used to store and manage data in the pre-big data world are so vastly different from how we do things today that I can't help but think of them as coming from an entirely different era. So, when I say old world, I'm referring to relational databases, even though those database systems are still around today. In the old world, we stored data in constructs that look like the spreadsheets that we're all used to working with. These constructs are called tables. If you wanted an efficient database for a transactional system, there were very specific rules about how you had to store this data. This set of rules we called normalization. The point of normalization was to eliminate errors that arose from inserting and updating data and to eliminate duplication of data as much as possible. Data were usually modeled as a set of relationships where a record in one table would relate to a record in another table. The relationships were set up as parent-child relationships, where a parent table would hold a record, and the child table would hold one or many records that were related to the record in the parent table. To ensure that the relationships were not broken, you would set up the table with certain rules. For example, a record could not be inserted into a child table without a related record in the parent table. The relationship that I just described is called a one-to-many relationship. One record in the parent table can have 0 to many related records in the child table. That is just one kind of relationship. There are several other kinds of relationships, but the 3 most common are one-to-many, as we've been talking about, one-to-one, where a record in the parent table can have one and only one record in the child table, and many-to-many, where several records in the parent table can be related to several records in the child table. Let's talk about keys. When working with data, it's important to be able to uniquely identify records. Uniquely identifying a record becomes really important when you need to delete data or join tables. When doing database maintenance, it frequently becomes necessary to blow away one and only one record. You have to be able to tell the database that this particular record and no other record is the one you want to delete. When we get to the labs, we won't be deleting data, but we will be joining tables. So, from the perspective of an analyst, it's important that you understand how tables are joined together so you can retrieve the data that you need for your analysis if that data happens to be spread across several tables. Just like relationships, there are several kinds of keys. For this class, you only need to be familiar with 2: primary keys and foreign keys. Keys are implemented as special columns that have rules on them that prevent the values in those columns from being duplicated. A key could be a single column or a combination of columns. In transactional systems, the values of keys can be arbitrary and implemented as an auto-incrementing number, or they might be meaningful like customer numbers or invoice numbers. In data warehouse systems, all the keys to tables are arbitrary. This is my personal belief, but I think that every single table should have a primary key. Out in the wild, I sometimes find tables that have been implemented without a primary key, and it always causes issues. Remember our discussion on relationships? This is where foreign keys come into play. In order to relate a record in a child table back to its parent record, you need the primary key of the parent table. When you're writing a SQL statement, this is how you join data together, as we'll see in a little bit. Let's take a look at an example of how keys are implemented. This is an Entity Relationship Diagram, or ERD for short. It's a diagram of a database. This diagram, in particular, documents the structure of Microsoft's AdventureWorks sample data warehouse. It's not the full warehouse, it's only the fact internet sales model. It captures all the facts and dimensions surrounding online transactions. We're not going to talk about the ins and outs of dimensional modeling. All you need to know for now is that facts are where we store numbers, and dimensions carry all the textual information surrounding the numbers. So a fact would be that a transaction came to $12.30. A dimension would carry the customer information for that transaction. As you may have gathered, the rectangles on the diagram represent tables in the database. Inside the rectangles is all the information about that table, such as table name, column names, data types, indexes, and whether a column is a certain kind of key. The convention of naming tables, starting off with what they are, fact or dimension, is a convention that I use when implementing warehouses. The broken lines on the diagram indicate relationships. I used Toad Data Modeler to draw this diagram and chose the option to use the crow's feet notation, since it's what I'm most familiar with. Crow's feet gets its name from how you indicate a many relationship. If you notice, most of the lines that touch the table fact internet sales end in a circle with 3 lines. This indicates that this is a many side of a relationship. If you trace the line back, you'll see it starts with a single perpendicular line. This translated means one and only one. This indicates the 1-2 side of the relationship. So using dim customer as an example, you say dim customer as a one-to-many relationship with fact internet sales. This should make intuitive sense as one customer has many transactions. As you may have figured out, this notation is also indicating that most of the dimensions are parents of the facts, making the fact table usually a child table filled with foreign keys, as we see is the case here. Take a look at dim customer again. You can see that customer key is the primary key of the table indicated by NNPK, meaning not null primary key. Plus, there is the obvious key next to the column. Now, if you look down at fact internet sales, you can find customer key, and that it's a foreign key indicated by NNFK in the gold key. And that is how you physically implement parent-to-child relationships in a database.